Variants of LU decomposition. हम LU decomposition मेथड से बखूबी वाकिफ हैं कि हम कोई भी मैट्रिक्स ए उसको डिकम्पोज कर सकते हैं इन टर्म्स ऑफ LU एज अ प्रोडक्ट फॉर्म। उसके बाद एक और डिकम्पोजिशन मेथड जो चोलिस्की डिकम्पोजिशन मेथड है उससे भी हम वाकिफ हैं और उसकी दोनों कैटेगरीज जैसे कि ए मैट्रिक्स को और ट्रांसपोज में डिकम्पोज किया गया था और उसकी दूसरी फॉर्म जो एल एल ट्रांसपोज के प्रोडक्ट्स में हमने सीखा था कि किस तरह हम डिकम्पोज करते हैं। एल यू डिकम्पोजिशन की एक फॉर्म है जो आज हम पढ़ेंगे। एन इम्पोर्टेंट वेरिएंट ऑफ द एल यू डिकम्पोजिशन इन द LDV डिकम्पोजिशन। ये डिकम्पोजिशन है ए मैट्रिक्स की तीन मैट्रिसेस के प्रोडक्ट की फॉर्म में। So let's start here. The statement of the theorem says that let A be an n cross n matrix whose leading principal submatrices are all non-zero. LU decomposition theorem at A be n cross n matrix whose leading principal submatrices. We all are well aware of this term leading principal submatrices. This is related with positive definite matrices, and if you see all the leading principal submatrices of A, they all are non-singular. Then A can be decomposed in exactly one way into a product A is equal to L, such that L is lower triangular matrix and U is upper triangular. Both are the triangular matrices, while L is unit lower triangular and U is upper triangular. In unit lower triangular, or we say that unit triangular matrix, the diagonal entries of the main diagonal of the given matrix is always 1. So L is unit lower triangular. This is the lower triangular matrix in such a form that its diagonal entries are 1, and U is any upper triangular matrix. For the proof, we see that we are aware of L and U already. We have to just show the uniqueness. Our uniqueness proof will yield to a second algorithm for calculating the LU decomposition. Look at the equation. A is equal to LU in detail. A is an n cross n matrix which is shown here, and it is decomposed, written as in the decomposition form of L and U, where L is lower triangular matrix with leading entries 1 1. Therefore we can say that it is unit lower triangular matrix, while U is any upper triangular matrix. The first row of L is known completely because there is only one entry which is unity. I mean that's 1. Other all entries are 0. And it has only one non-zero entry multiplying the first row of L by the jth column of U. You can take any column of U and multiply first row of L with the jth column of U according to the multiplication rule. A1j can be written as described because this only element is non-zero, other all entries of L matrices in first row are zeros. Therefore, if you want to write it in its complete form, you will write it as that is U1j is equal to Aij. U1j is equal to Aij can be deducted from the above result because other all entries are zeros. Thus, the first row of U is uniquely determined. You can easily determine the first row of the U matrix because U11 is equal to A11, U12 is equal to A12, U13 is equal to A13, and you are aware of all the entries of A matrix. Therefore, you can find all entries of first row of U matrix. Now we know the first row of U. We see that the first column of U is also known. It since its only non-zero entry is U1. We have found the first row and the first column of the U matrix. Now multiplying the ith row of L by the first column of U, we obtain this result. You take any row of the L matrix and multiply the first column of U. This simple result will be gained. If you vary I from 2 to n, you can find all the values. The assumption that A is non-singular implies that U is also non-singular. Trace the result here. Why we say this? Hence UKK is not equal to 0 for k is equal to 1 to n. All entries in the main diagonal of the matrix U are non-zero. And in particular U11 is not equal to UK. Therefore, the first column of L can be found uniquely from this result. Here you have to vary the I, which varies from 2 to n. You will find all the values of first column of L because you know AI1. All the entries of A matrix in first column. If you vary I as 2, 3, 4, 5, you have these values AI2. And similarly, U11 is already determined, which is A11. Therefore, you will find Li1. I varies from 2 to n. So you have found all the entries of the first column of the matrix L from this result. Thus, the first column of L is uniquely determined. Now that the first row of U and first column of L has been determined, it's not hard to show that the second row of U is also uniquely determined. As an exercise, determine a formula for U. It is up to the student in terms of A to J. you will try to find a main formula for U2J as U1J or Li1 and entries of the first row of U and columns of L. Once U22 is unknown, it is sorry. Once you will find the U22. When it is known, it is possible to determine the second column of L. As here it is written, you have to do it as an exercise. You will easily do this. Now suppose the first k minus 1 rows of U and columns of L have been shown to be uniquely determined. We will show that the kth row of U and column of L are uniquely determined. This will prove uniqueness of the induction. The kth row of L is this, since are all in the first k minus 1 columns of L. The kth row of L is this, LK1, LK2, here it is 1, the diagonal entry, and these entries are all in the first k minus 1 columns of L. They are uniquely determined. Multiplying the kth row of L by the jth column of U, we find this result. Using the preceding entries, we can find all entries of the matrix L and U. Because all of the U and J lie in the first column, first k minus 1 rows of U and are therefore known. Therefore, UK is uniquely determined by the last relation. With the help of last relation, you can find UKJ. This proves that kth row of U is uniquely determined and provides a way of computing it. Now that UKK is known, the entries of kth column of U is determined. Multiplying the ith row of L, we find that AIK as in the form of summation. All of the LIM lies in the first k minus 1 columns of L, just as you have find the U entries of the U, you can find the all entries of L matrix with this relation. This proves that kth column of U is uniquely determined and provides a way of calculating it. The proof of L and U are unique is known. Try to write down each and every step, each and every term. You will easily understand this relation, these all relations, and from these all relations you can find the all entries of L and U matrix. The theorem we have discussed earlier will be helpful here. LDV decomposition theorem, which is the variant of LU decomposition. Actually, we want to study this theorem, and for the help we discussed the previous theorem. This theorem states that AB an n cross n matrix whose leading principal submatrices are all non-singular. Then A can be decomposed exactly in this product form. If any n cross n matrix which has leading principal submatrices non-singular, then it can be decomposed in uh, the product form of three matrices, where L is unit triangular matrix, D is diagonal matrix, and V is unit upper triangular matrix. Here V is also a unit triangular matrix as L is unit lower triangular matrix. And the diagonal matrix is very easy. You know that only it consists on diagonal entries. Let's start the proof for A is equal to LDV. The theorem mentioned here 1.7.19 is the same theorem as we have discussed here earlier. This theorem says this unit lower triangular and L and upper triangular U such that A is equal to only L was the lower unit triangular matrix. Since U is non-singular, therefore the diagonal entries are non-zero, which is written here UKK is not equal to 0 for K varies from 1 to n. Let D be the diagonal matrix whose main diagonal entries are U11, U22 and so on up to UNN. Then D is non-singular. D inverse is the diagonal matrix whose main diagonal entries are of this form. We know we can calculate the inverse of diagonal entries very easily. We get the reciprocal of all the diagonal entries of the D matrix, we obtain D inverse. If you want to find the inverse of the D matrix, you will see that the all entries of D inverse, the new matrix, will be the reciprocals of the given matrix D. Let V is equal to D inverse U. D inverse D has the same values in the diagonal as U have the diagonal entry. Therefore, D inverse has the reciprocal of the diagonal entries of the U. You can easily check that V is a unit upper triangular. Why V is unit upper triangular? Because V is the product of D inverse U. D inverse consists on all the entries in the diagonal or the reciprocal of the entries of the diagonal of U matrix. And A can be written as A is equal to LDV. We have A is equal to LU and U is decomposed here. V is considered as D inverse U, therefore A can be written as LDV. To complete the proof, we must show that the decomposition is unique. Suppose A can be decomposed in two such forms. A is equal to L1 D1 V1 and A is equal to also L2 D2 V2. Let U1, let us discuss it. First, A is equal to L1 D1 V1, then U1 is equal to D1 V1, because u here u is here v is d inverse u and u is equal to dv. We come here d1 v1 will be equal to u1, and similarly if we consider a is equal to l2 d2v, then u2 is equal to d2v2. Then obviously u1 and u2 are upper triangular. u1 and u2 are upper triangular matrices, and A is equal to L1 u1 and A is also equal to L2 u2. By the uniqueness of LU decomposition, which we have already proved, L1 will be equal to L2 and u1 will be equal to u2, because we have jumped into the decomposition A is equal to Lu, and we have already proved that this decomposition is unique. Therefore, A is equal to L1 U1 is equal to L2 U2. And from this result, we obtain that L1 U1 is equal to L2 U2, and therefore L1 is equal to L2 and U1 is equal to U2. The later equation implies that d1 v1 is then equal to d2 v2. If d2 d1 v1 and d2 v2 are the same, then we can write it as in this form. We combine the diagonal matrices and the v matrices. From this result, let's move ahead. Since v1 is unit upper triangular, so is v1 inverse. If v1 is unit upper triangular matrix, therefore v1 inverse is also unit upper triangular. Since v2 and v1 inverse are unit upper triangular, so their product is also. On the other hand, d2 inverse d1 is clearly diagonal. Thus, the last theorem says that v2 v1 inverse is both unit upper triangular and diagonal. Therefore, v2 v1 inverse is equal to identity matrix. If it is the product which is equal to identity matrix, then these two matrices will be equal. And similarly, d2 d1 are the same. This proves the uniqueness of the theorem. Here is another theorem which states that A be positive definite matrix. A is any matrix which is positive definite matrix, and you know the definition of positive definite matrix. Then A can be expressed in exactly one way, or the product M D inverse MT, such that M is lower triangular, D is diagonal matrix whose main diagonal entries are positive, and the main diagonal entries of M are the same as that of D. Diagonal entries of M and D are the same and positive. If A is positive definite matrix, it can be written as A is equal to M D inverse M transpose in this relation. We start with this decomposition that we can write A as in term of LD LT. Let A is positive definite matrix. Therefore, it can be written as in the form of LD LT. And now we assume that M is equal to L. Let M is equal to L. Then clearly A is equal to M D inverse MT. If A is equal to LD LT and we let that M is equal to LD, we can find the value of L matrix from this relation. L will be equal to MD inverse. L will be equal to MD inverse, which is written here. Let's take the inverse of L transpose. L transpose will be equal to MD inverse whole transpose. And the transpose property says that it is equal to D inverse transpose M transpose. D inverse transpose is equal to D inverse MT. Therefore, D inverse MT is equal to L transpose, which is replaced. This L transpose is replaced with D inverse MT. The proof of uniqueness is left as an exercise. आपके पास चंद मिनट्स हैं, ये जो अभी थ्योरम हमने डिस्कस किया है इसको स्टेप वाइज आप नोट करें। 6-7 स्टेप्स बनेंगे, बहुत आसान